Continuing section 9.1, the action of forces and torques on rigid objects, let's look at an example of the Achilles tendon. The tendon exerts a force of magnitude 720 newtons. Determine the torque, magnitude, and direction of this force about the ankle joint. The distance between point P and the ankle joint is 0.036 meters, and the tendon is at an angle of 35 degrees relative to the horizontal. All right, so let's see if we can figure this out and hope that this tendon doesn't prove to be our Achilles heel, our undoing, but I'm confident that we can get it. So first, let's jot down a few things that we know that are given to us in the problem. And I made an image so that we can work with that picture because I think that will be helpful to us here. So first, it tells us the tendon exerts this force of magnitude 720 newtons. The other thing we want to think about with that force is we know it acts at point P, but what direction does it act? Well, the key thing with muscles is that they can always contract, right? They're always pulling. They create tension. They aren't able to push. When you're pushing, it's actually other muscles that are contracting and pulling. So that means the Achilles tendon at point P is not going to be able to push point P. It's going to pull on point P to lift that heel. I'll make that even bigger, actually. 720 is a lot of force. Right, so we have that force, and I'll make this whole image bigger in a moment. Stop sharing. Distance between point P and the ankle joint is 0.036 meters. And then they tell us that the tendon is at this angle of 35 degrees relative to the horizontal. So we notice that if the tendon muscle is along the direction of the force, we can say that this angle then is 35 degrees. All right, and we want to find the torque about the ankle joint. Great. Notice it says with the torque, it's magnitude and direction. So we'll keep that in mind. All right, so now this is a little bigger, a little easier to see. As we think about our tools, we just learned how we can calculate torque, the magnitude of it at least. And the magnitude of the torque, we said, is the force times the lever arm. We already know our force, 720 newtons. So that part's pretty slam dunk. What about the lever arm, though? Do we know that? Well, we do know this distance, 0.036 meters, but is that the lever arm? Let's check. Notice it's at an angle of 35 degrees relative to the pulling force. That's not a perpendicular angle. That means we need to draw in our lever arm. And that lever arm is going to go from our axis of rotation to the line of action. All right, so our line of action is going to be anywhere along this force. See, I'll get a light blue again. It could be anywhere before the force, anywhere along the force, anywhere beyond it is our line of action. And then to draw our lever arm, we're going to need to first identify our axis of rotation. What's our axis of rotation? Well, notice we have a clue in the problem where it says to calculate the torque about the ankle joint. The ankle joint is what everything else is rotating around. So that's going to be our axis of rotation. So if we imagine starting at this point, the ankle joint, we need to find a perpendicular intersection with our line of action. If we go anywhere lower, this angle is getting really large. If we go beyond the force, that angle is really small. So it's somewhere in between it looks like it'd be about there, right? I'm able to line up the tick marks on my ruler with the line, so that's a sign that it's perpendicular. It's lined up with my ankle joint, which is the axis of rotation. I fill this in here. Yeah, we notice that is indeed at a right angle. So that will be our lever arm L. Now, if we want to find L, how can we do that? This is where we're going to use our trigonometry again, right? Notice, since we have that right angle, we have a triangle that we can solve for the lever arm using the other angle than the 90 degrees, 35 degrees, and this 0.036. So first, we need to identify the sides of the triangle. So if we use this angle of 35 degrees, then what's the hypotenuse? Well, the hypotenuse is going to be the longest side of the triangle. The longest side of the triangle in this case is the bottom of it, this 0.036. The lever arm is now the opposite side. So if I want to find something with the opposite side in the hypotenuse, that's going to be sine. So sine 35 degrees is equal to the opposite L divided by 0.036 meters. So in other words, my lever arm L, 0.036 meters times sine of 35. Incidentally, the book decided instead to label the other angle. They labeled the angle between the 0.036 and the L. And so that angle is 55 degrees. And it turns out you could use the 55 degrees as well. You would just then need to use cosine of 55 instead. So cosine of 55 degrees is equal to L, the adjacent side over the hypotenuse, 0.036 meters. And you get the exact same result. You can try this on your calculator if you're in doubt. 0.036 meters times cosine 55. Whichever way you calculate it, you'll get the same thing. So they are equivalent. It's whatever you prefer. Once we know this lever arm, we can plug it into our torque equation, and we're basically home free. So torque is equal to the force times the lever arm. So the force is that 720 newtons, as we wrote up above. And then the lever arm, 0.036 meters sine 35 degrees. So if you calculate that out, you should come up with a number that is like 15. And what would the units be? The units of torque, remember, are force times a distance, so that would be Newton meters. All right, so this is looking good. Are we done now? There's one more thing to think about, and that's that this is just the magnitude of the torque. We still need to fill in the direction if it's in the positive or the negative direction. To do that, we need to pay attention to what kind of rotation this torque is causing about the axis of rotation. So in this case, if our ankle joint is the axis of rotation, this force would cause it to rotate, notice that would be in the clockwise direction. So since the rotation relative to the axis is in the clockwise direction, this is going to have to be a negative torque. So that's something you need to fill in when you're solving these problems. To include the direction, you need to add that negative sign. Because it is causing clockwise rotation. Pull that down a bit. And just to highlight how the book solved it, we can go back to that for a moment. Here we go. So here you see that they had the 55 degrees labeled instead of the 35 degrees. So the book used cosine of the 55. But sure enough, they got the same answer of 15 Newton meters, which is just the magnitude. Because of the clockwise rotation that it would cause, the torque is negative 15 Newton meters. There's an example of using torque in practice, and we'll get to see in the next section how torque can be combined with our understanding of forces and Newton's second law in order to solve a lot of different problems in static equilibrium.